some of you may be saying to yourself, okay, well, these conditional things, these B's and A's and B's, do they really matter the order in which I do them? So let's take a look. So if you go back to the table and consider this, does the probability of B given A equal the probability of A given B? So in other words, does the probability of choosing sports given you're a girl equal the probability of being a girl given they chose sports as what they wanted to excel at? So let's use the formulaic approach to this to see if we can see whether or not these two are the same thing. So in the first, on the left-hand side, the probability of sports given girl would be the probability of sports intersect girl divided by the probability of girl. And we want to see whether or not that is equal to the probability of girls intersecting sports divided by the probability of sport. So we're going to need to go back to the table and get some of these values. So why don't you pause it, go back, and see if you can fill in the numeric values that go into our fractions, and we'll determine whether or not these two things are equal. Alright, so these are the values that I got. The numerator of these two conditional probabilities are the exact same thing, because the intersection of sports and girls and sports are the same intersection. It's 30 out of the 478 total participants. But the denominators are different. The probability of girl on the left-hand conditional is this 251 out of 478. That's the 251 females out of the 478 total participants. On the right, though, the probability that you chose sports as your goal is 90 out of 478. So now I need to see, are these two equivalent? They have the same numerators. They would need to have equivalent denominators for them to be equal to each other. So right off the bat, if you just investigate this, is it possible that 251 478 is equal to 90 over 478? And in fact, they are not equal to each other. I could simplify the fractions for you just to make it a little clearer. So this left-hand fraction simplifies to 30 over 251. This right-hand fraction simplifies to 30 over 90. And again, numerators being the same, 251 and 90 are completely different numbers, so there is absolutely no way that these two are equivalent to each other. So in most cases, and I know that Ray Tien is sitting in the back row right now, coming up with the case in which B given A and A given B are going to be exactly the same. And yes, there are cases where that will work, but you have to be careful moving forward, making sure you know what your B and your A are, and making sure that you're doing them in the right order. Because you may feel like you're doing the conditional correctly, and the setup would be correct, but if you have the wrong denominators, you're going to get the wrong answers. So be really, really careful of that moving forward. All right, so here's another example. We talked about this earlier with the 56, 62, and 42. It was one of our early examples. While dining in a campus facility open only to those with meal plans, you meet someone interesting. What's the probability that this new acquaintance lives on campus? Okay, so you've met someone while you're eating. You want to know what's the probability that they live on campus. So this is a conditional probability because the only way in which you're meeting this person is under the condition that they have a meal plan also. Or I guess they could have snuck into the campus facility to eat, but let's just assume they're on the up and up and they didn't do that. So I am trying to compute in this problem, what is the probability that they live on campus given I know they possess a meal plan? Well, formulaically, what we're talking about is the probability of L intersect M divided by the probability of M. So if I can figure out what that intersection is and I can figure out what that probability of having a meal plan is, I'll know it. And these pieces of information are told to us in the problem. We're given that the intersection of living on campus and having a meal plan is 42%, so 0.42 in the numerator. And we are given that those who have the meal plan have a probability of 0.62. It's this one over here. Let me erase that. It's over here. 62% have the meal plan, so 0.62 in the denominator. And taking 0.42 and dividing it by 0.62, I get the probability of L given M as 0.677. So the likelihood that this new acquaintance lives on campus, a little higher than 67% chance. All right, so that's how we're going to be using this. Again, formula-wise, if you can write out the conditional and you know the rule, should be able to just slip the numbers in and get the answers out. So for this final example, number 5, I'd like you to take a second and again read through and really try to make sense of the wording of these problems. This is where probability gets a little confusing because sometimes it looks like they're asking the same question several different ways when in fact they're asking for 3 completely different probabilities. So I urge you again, in the couple of minutes that you're going to take to do example number 5, try to first write a probability statement as to what you're trying to find and then find the probability. Don't try to just write down numbers. All right, take a few minutes, do it, and then when you're done, come back here and you can check your answers. There's no way you're done already. Seriously, come on, man. You got to do the problems out. Pretend like I'm here and I'm just like leaning over your shoulder and making you feel guilty for not doing it. So take the calculator out, start writing some stuff down, and check your answers. If you're back that soon, I'm guessing you need a hint. So here are the 3 probabilities you're being asked to find. Probability that you're male and a supervisor for part A. Probability that you're a supervisor given you're a male in part B. And the probability that you're male given you're a supervisor in part C. All right, so now take those and see if you can formulaically make them work for you. So here are the 3 values you should have gotten, and let's go through them to make sure you get it. Probability that the employee is a male supervisor, so male and being a supervisor, is right over here. There's only 8 of them that we have to worry about. And if you added the table up, you realize that there were 150 total people in the survey. So 8 out of 150 gives you the value of 0.053. So there's your male supervisors. The probability that you're male given you're a supervisor uses the same value in the numerator, that you're a male and you're a supervisor, but now you're restricted to only males. And there are only 60 males in the column. So 8 out of 60 gives you the 0.133. And then if you flip the conditional and you do males given supervisor, still the same numerator. Supervisors and males are 8, but now you're dividing by just the total number of supervisors, of which there's only 8 plus 12 or 20. So 8/20ths gives you 0.400. All right, so these are the examples that are taking you through the first set of conditional things. We're going to talk about independence and conditionals in the next video. But in the meantime, make sure you get the work done that you need to get done. Make sure you're not giving Miss Wong a hard time. I miss you all. I'll see you soon. Bye.